So let's finish up the 5.1 section from Hong, Wang, and Gardner. We're shifting gears a little bit here and starting to address types of bases for vector spaces or linear spaces. Since finite dimensional vector spaces are totally classified in the fundamental theorem of finite dimensional vector spaces, we'll now turn our attention to infinite dimensional vector spaces. Now, the change we'll make is, in a sense, rather minimal. We'll modify some definitions: basis, span, linear combination. It's really just linear combination that we'll explicitly modify, and that'll have implications for these other things. If, though, we stay the course and insist on the same kind of definitions you have in sophomore linear algebra, the big one being that when we say linear combination, we mean finite linear combination. Such a basis, what we simply call basis in the past, such a basis is called a Hamel basis. We're going to show every vector space has a Hamel basis, something you didn't address in sophomore linear algebra. Yeah, but they're your vector spaces. They were always Rn, possibly Cn, but they had the most obvious basis, the standard basis, the vectors of ones and zeros. So we're in potentially a much more complicated setting in this course, and this idea of a Hamel basis will be showing that any vector space has a basis, a linearly independent spanning set, and the requirement here will be the usual thing that every vector is written as a finite linear combination of the basis vectors. Maybe the surprise is the argument to prove this requires something equivalent to the axiom of choice called Zorn's lemma. It's really just a set theoretic argument. So we're going to have to step aside here briefly and discuss some set theoretic ideas. First, for set X, any subset of the Cartesian product of X with itself, so these would be ordered pairs of elements of set X. Any subset of the Cartesian product of X with itself is called a binary relation on X. And such a relation, we'll call it R, is said to be reflexive if, for all X in the set capital X, the ordered pair X comma X is in the relation. It's the way properly to word it, because we've described the relation as a subset of the Cartesian product. Of course, the better way to think about it is this means X is related to X, maybe X capital R X, you might write notationally. Relation R is symmetric if, when X is related to Y, we get Y is related to X, or when we have the ordered pair XY in set R, we also have the ordered pair YX in set R. And R is transitive if, when ordered pair XY is in R and ordered pair YZ is in R, then we get ordered pair XZ is in R. Thinking of it in terms of relations, more hands-on, we'd say something like if X is related to Y and Y is related to Z, then X is related to Z. So that makes it a little easier to remember. We're interested in specific kinds of relations. A relation R on a set is an equivalence relation if it has all three of those properties we just defined, if it's reflexive, symmetric, and transitive. A relation is anti-symmetric if X and Y being in R and Y and X being in R implies that X equals Y. So if X is related to Y and Y is related to X implies X equals Y, then the relationship is anti-symmetric. An example of which would be something like less than or equal to on the real numbers. We'll use subset inclusion usually to determine our relations. A relation is a partial ordering if it's reflexive, anti-symmetric, and transitive, and we'll denote it with the less than or equal to symbols. A relation is a total ordering if R is a partial ordering and for any elements of set X, either X is, let me read it as less than or equal to, X is less than or equal to Y, or Y is less than or equal to X. So in a partial ordering, we may have X's and Y's that aren't comparable. We may have neither of these occurring in a partial ordering, but in a total ordering, any pair of elements of set X are comparable in the sense that one or the others of these holds. If set X is partially ordered with a less than or equal to notation, a maximal element of the set is an X, lowercase x, in the set such that the condition X less than or equal to Y implies Y equals X. So X being maximal means there's nothing greater than or equal to X, if I read this in that sense. The condition X is less than or equal to Y has to imply Y equals X. So an element is maximal means, a touch more informally, there's nothing greater than or equal to that element. There may be some things not comparable to it, partial ordering, but there's nothing greater than or equal to that. And similarly, X is a minimal element if the condition Y less than or equal to X also implies Y equals X. So in this case, X is minimal, nothing is less than or equal to X. We get an element less than or equal to X, that element must in fact be X itself. So maximal and minimal should be interpreted like that. There's nothing greater than or equal to a maximal element other than the element itself. And there's nothing less than or equal to a minimal element other than the element itself. There may be things not comparable because we're dealing with a partial ordering. And a set E can have an upper bound if we take an element X such that Y is less than or equal to X for all Y in the set. So this point X, this element X, is then called an upper bound for set X. We could similarly define lower bounds for a given set, if such an X exists, of course. The following, Zorn's lemma, is equivalent to the axiom of choice. We'll talk about the downside of that here shortly. But the statement of Zorn's lemma is, if X is a partially ordered set and every totally ordered subset of X has an upper bound, then X itself has a maximal element. If X is a partially ordered set, and, so here's what we'll need to address to use this, every totally ordered subset of X has an upward bound, then X itself has a maximal element. Okay, so maximal elements is how we're going to access these Hamel bases. So what we'll have to do is define a partial ordering on an appropriate set. And with respect to that ordering, we'll have to show that every totally ordered subset of X has an upper bound. From that, we'll be able to conclude that X has a maximal element. By Zorn's lemma, that maximal element will be the basis that we're looking for. So the formal definition or statement of the existence of a Hamel basis is as follows. Let VF be a vector space, then there exists a set of vectors, B, a subset of the vector space V, such that first, B is linearly independent, and second, for any vector in the vector space, there exists a finite set of vectors, a subset of set B, and a corresponding finite collection of scalars, such that vector V is a linear combination of that finite collection of vectors from the basis with that given collection of scalars as coefficients. In other words, B is a Hamel basis. So we're getting a linearly independent set of vectors, and any vector can be written as a linear combination of some of those vectors. That's a spanning set. It's a linearly independent spanning set. This collection B is a Hamel basis for the vector space. All right, so the proof will involve Zorn's lemma Actually, the proof is surprisingly short given all the set theoretic stuff and the content of it. We'll define P to be the class whose members are linearly independent subsets of V. Then define the partial order on P as A less than or equal to B means A and B are both in this class and A is a subset of B. It's common to define partial orderings using subset inclusions. And you can see how there might be certain sets in this class of linearly independent subsets of the vector space, which wouldn't be comparable. So that's easy enough to conceive in this setting. So we have class P defined. We have the partial ordering on that class defined. First, it's a non-empty class. If we take a non-zero vector, the set consisting of that single vector itself, that forms a linearly independent set. That's not the zero vector. A single vector forms a linearly independent set. So this class of sets of linearly independent vectors, it's non-empty. So this P collection is non-empty. Next, suppose Q is a totally ordered subset of P. All right, so here comes the totally ordered subset. We wish to find for Q an upper bound. Then we can use Zorn's lemma to conclude there's a maximal element of this class P. So suppose Q is a totally ordered subset of P. Define M, for kind of like maximum, to be the union of all of the sets in Q. So we're unioning up all sets in Q. Well, then M is an element of P. Q is a totally ordered subset of P, meaning we've got a collection of linearly independent sets. They're nested because of the partial ordering thing. By the totally ordering thing, and which we're taking as subset inclusion. So we have, I want to think of it as a string of sets, but nothing gives me the right to assume countability in any of this stuff, like a first and a second and so forth. There is some kind of ordering on the thing. But we'll simply union up all of those sets in Q, creating M. It'll be an upper bound of Q. It'll be linearly independent, and the union will be greater than or equal to all of those constituent sets in this totally ordered subset Q. So we have the upper bound, M, the union of all of the sets in totally ordered subset Q. So this is an arbitrary, totally ordered subset. It has a maximal element, an upper bound, I should say. So by Zorn's lemma, then the whole collection, P itself, has a maximal element. Call that maximal element B, because it's going to be the basis, the Hamel basis. B is in P. That's part of the story. Hamel's or Zorn's lemma gives you an element of P that's maximal. So B is in P, meaning B itself is linearly independent, because P was a collection whose members are linearly independent subsets. So B itself is a linearly independent subset. Also, it's maximal is the claim. If V is any vector, or excuse me, it's maximal from Zorn's lemma, we need to show it's a spanning set. That's what we need to do. So if there's any vector V in the space, must be a linear combination of the elements of B, and so in the span of V. So we've taken an arbitrary vector V, we're claiming it's in the span of set B, giving us the spanning set property. Because if it ain't, then if we'll look at the set B union this other vector over here, that would also be a linearly independent set, and that would be a superset of set B. So it'd be something bigger than the maximal element, and there is nothing bigger than the maximal element. So vector V must, in fact, be a linear combination of the elements of B. That is, B must be a spanning set. So linearly independent spanning set, why, that's a basis. And all of this dealt with in terms of these finite linear combinations. Must be finite linear combinations in vector spaces unless you have some additional structure, and we're not there just yet. So every vector space has a basis in the sense defined in sophomore linear algebra. Something you didn't show in sophomore linear algebra. Yeah, well, there's why. Zorn's lemma is why you didn't get into this in sophomore linear algebra. And the vector spaces you dealt with were pretty hands-on vector spaces in linear algebra. Now, this next claim is quite similar to something we did earlier. Earlier, we showed that in a finite dimensional vector space, any two bases are the same size, same cardinality. We're going to show that holds in arbitrary vector spaces. So what we're going to show is stated as an exercise in the Hong-Wang-Gardner book. It says if B1 and B2 are both Hamel bases for a given infinite dimensional vector space, then B1 and B2 are of the same cardinality. That's what we did in finite dimensions. Here, just explicitly doing it in infinite dimensions, and again with Hamel bases. And so we could potentially define dimension using the cardinality of a Hamel basis. I'm not sure how useful that is in these more abstract spaces. It's certainly useful in finite dimensions. It's useful in some infinite dimensional spaces. I'm not sure how useful it is in some of the more weird ones. But two Hamel bases have the same cardinality as the claim. And we're going to need a little bit more set theory to get through this. Taking two results from Hungerford's Algebra. This is the book we use at ETSU in the graduate modern algebra sequence. A couple of results from that reference from the introductory chapter, chapter 0. So that's the numbering. One is the Schroeder-Bernstein theorem that says if A and B are sets such that the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then the cardinalities of A and B are equal. Not to get too into the weeds on the set theory, but each of these statements are statements about the existence of some kind of functions. A can be mapped one-to-one into B. B can be mapped one-to-one into A. There's a bijection between A and B. So each of these claims has a corresponding claim about the existence of a certain kind of mapping, a one-to-one mapping, an onto mapping, or a bijection, a one-to-one and onto mapping. Not a surprising claim, but something that needs to be established, this being really only interesting in the setting of infinite sets. So this allows us to set up idea of cardinal numbers as well. If J is an infinite set, and for each I in J, set A sub I is a finite set, then the union over all lowercase j and set capital J of these A sub j's, the cardinality is less than or equal to the indexing set J itself. So the idea here is, in some sense, for every index, think of J as an indexing set. It certainly is here, the way we've used it here. J is an indexing set. For every index in J, there's associated a little finite set. When you union up all those little finite sets, you get a set that results with cardinality less than or equal to the indexing set. That might seem a little logically offensive to you, but not an odd thing to claim about infinities. Infinities behave in initially unexpected ways. Also, nobody said these sets A sub I, they could be empty for all I know. Empty sets are finite for one thing, and they could overlap with each other for all we know. But there's the claim. Thinking of these in terms of indices is how we'll use this exercise, so-called exercise 0.8.11. This is how we'll use this in a proof that two Hamel bases have the same cardinality. So now we've got the equivalent to prove any two Hamel bases are of the same cardinality. So the proof is going to be actually kind of like the proof we had in finite dimensions. So suppose we have two bases, b sub 1 and b sub 2. Take b sub 1, consider the vectors in that Hamel basis to be vector b sub I, where I ranges over some indexing set. Right? Don't read into this finite, of course. Don't read into it countable. Don't read anything into it. How many basis vectors are there? I don't know. However many indices there are. So B1 has this set capital I as an indexing set. And so the cardinality of B1 is the cardinality of the indexing set. For every basis vector, there's an index. That's all that means. Now let's go over to the other basis. What we're going to do is write the elements in the second basis, let me call it b sub 2. We're going to write the elements of b sub 2 in terms of the elements in b sub 1. We're going to write these vectors as linear combinations of these vectors. And then we'll flip the roles of b1 and b2 right at the end and reverse an inequality. So for any vector u in b sub 2, we have that u is a finite linear combination of some finite subset of basis b sub 1, because basis b sub 1 is a basis. And we're talking Hamel basis here, so of course finite linear combinations. So vector u can be written as a sum of some finite collection. So we're introducing this set j sub u of indices from set I, and it's a finite set. So here comes a collection of finite sets, which we'll use that exercise on. But we get some finite collection of indices such that we get scalar multiples of the b sub i's, finite number of these, got to be finite, Hamel basis. And we can write any vector u in basis b sub 2 as a finite linear combination of the vectors in b sub 1. What we're really interested in is the fact that we're going to use some of those indices, and those indices are going to be in set j sub u. The u coming from the fact we've used vector u from basis b sub 2. The j sub u's are all subsets of set I. They're indices on the b's, right? B sub I. So the i's are indices on the b's. They're some elements of set capital I, indexing set capital I. So each j sub u is a subset of I. As I repeatedly iterated, let me reiterate it, they're all finite because we're dealing with finite linear combinations. That's what a Hamel basis is. So we got ourselves a giant collection of finite subsets of set I. So consider what you get by taking a union of all of those j sub u's as u ranges over basis b sub 2. So this would be all of the indices from I that are necessary to write all the elements of basis b sub 2 in terms of b sub i's. So it gives you, in a sense, which of the b sub i's are required to write all of the elements of the second basis in terms of those b sub i's. Not surprisingly, it's going to take all of them, is what we'll ultimately show. Certainly we have j as a subset of I. I mean, each of the j sub u's is a subset of I, so when you union up a bunch of them, you get something that's a subset of I. That's just the setting, the construction. Suppose they ain't equal. Suppose it doesn't require all of these basis elements to write all of the basis elements in basis B2. That is, assume j does not equal I. We know j is a subset of I, so this must mean there's something in I that's not in j because of the subset inclusion. Inequality of the sets implies there's some I prime, an index in I, where I prime is not in j. Now, consider vector b sub I prime. Okay, it's a subscripted b. It's one of these. It's a basis element in b sub 1. This is in the vector space. B2 is a basis for the vector space, so this particular vector can be written as a linear combination using basis vectors from basis B sub 2. So we're shifting gears here, writing this in terms of the second basis elements. That is, B sub I prime is some linear combination, sum over indexing set K of F sub K, C sub K. K must be a finite set because we're only doing finite linear combinations because we're talking Hamel bases. And we're taking the C sub K's from the second basis this time. Not all the F sub K's are 0 because B sub I prime is an element of a basis. You can't have the 0 vector in a basis. Messes up linear independence. So set K itself is also a finite set. All right, so we've got B sub I prime written in terms of these C sub K's. There's just a finite number of those C sub K's. The C sub K's are in B sub 2. Now, you know anything in B sub 2 can be written in terms of the B sub i's. U is an element of B sub 2, then U is some sum of the B sub i's. Actually, it's the sum over these indices here. I know which B sub i's are required. You want to write C sub K in terms of B sub i's? Use indices that we would denote as I sub J, I an element of J sub vector C sub K. J sub C sub K is the indices that would be necessary to write C sub K as a linear combination of these. So we're going to give an argument that's really heavy on basis B sub 1. We haven't touched basis B sub 2 except in this notation here, at least so far. But like I said, in the end, we'll interchange the roles of B1 and B2. So they end up playing equally important roles. So let's take all this linear combination, take these C sub K's and write each of them in terms of B sub i's. Next slide. We've taken C sub K and we've written it in terms of the B sub i's. Which indices is this going to require? The indices in J sub C sub K, J sub vector. The vector we want to write here is the vector C sub K. Okay. Then that'll require indices in set J sub that vector, J sub C sub K. So we still have a sum, finite sum, F sub K times the C sub K's. We've just expressed the C sub K's in terms of basis B sub 2. The F sub i's are non-zero. Some of them are non-zero because we're not dealing with a 0 vector. These were basis vectors as well. This is not a 0 vector. The F sub K's, some of those are non-zero of necessity as well. A quick observation, I prime is not in J. That was the assumption that I and capital J are different indexing sets is what led to the existence of this I prime. So when we look over here on the right, these are subsets of set J. So none of these are I prime. There's not a B sub I prime in any of this on the right-hand side. There is on the left-hand side. So there's no B sub I primes on this side. I prime's not in J. That index is not used in this summation. And so B sub I prime is none of these over here. But then we've got B sub I prime written as an elaborate but finite linear combination of some of the B sub i's. And we just messed up linear independence. And that's where the contradiction will come from. Or if you like, I can subtract this B sub I prime from both sides, giving us a 0 vector on this side and giving us a linear combination of a finite number of the B sub i's on the other side. And some of the coefficients are non-zero. So that's a problem as well. That's a problem with linear independence. So what we get from this then is that the finite collection of vectors, B sub I prime, and all the B sub i's that are used here, and symbolically, here's what it is. That finite collection of vectors is not linearly independent. That finite collection of vectors is linearly dependent. But then that contradicts the fact that the set B1 is a basis, a linearly independent spanning set. So you can't have linear dependence on a finite subset. And that's how linear independence is defined in general. So we've contradicted the linear independence stuff by establishing a linear dependence. Well, it's contradiction. So what we assumed must be wrong. We assumed J and I were not equal. So now we can draw the conclusion that J equals I. Now, for each J sub U, remember that was indices required to express vector U in terms of basis elements in basis B sub 1. But each of those is finite. Exercise 0.8.11, the exercise that dealt with collections of finite sets. I told you we were going to use that in terms of the indices. What that will give us then is basis B1 was the same as a cardinality of I. That's one of the first things we said. We just argued that I and J are equal sets, so we get equalities in their cardinality. J was, if you'll look back, maybe we'll go back and find this, set J was the union of all of these things here. Let's go back and find that. Clicking back, probably 2 slides. There it is. We define J exactly as this, a union over all vectors in B sub 2, the J sub U indices. Okay, so these are equal. The sets are equal, so the cardinalities are equal. And what we're doing here is for every vector in B sub 2, call it U, we're associating it with a finite set, the set J sub U. And the exercise said when you do that, for any set here, you associate a finite set here and union them up. This collection and cardinality is less than or equal to the cardinality of the indexes, effectively is how the exercise, I think, was laid out. But it allows us to draw this inequality. So, big picture, we've got B1 is less than or equal to B2. And we did this by writing some of the basis elements in terms of other basis elements. And that's how we did it in finite dimensions. We didn't need all the set theory stuff in finite dimensions. But there's similarities between that proof and this proof. So we've drawn the conclusion that B1 is less than or equal to B2 in cardinality. Interchange the roles of B1 and B2, and we reverse that inequality. We get B2 is less than or equal to B1. The Schroeder-Bernstein theorem says when you have cardinality of B1 less than or equal to cardinality of B2 and cardinality of B2 less than or equal to cardinality of B1, then the cardinalities of B1 and B2 must be the same. And that was the claim. B1 and B2 are of the same cardinality. So, Hamel bases, you got 2 of them for a given vector space, they will be of the same cardinality. Other things about Hamel bases, they're not at all practical. So, we use Zorn's lemma to establish the existence of a Hamel basis. We got some nice behaviors out of them with this, same cardinality thing. But the fact that we had to resort to using Zorn's lemma tells you that Hamel bases exist, but it does not tell you how to find them. We do a similar thing in measure theory, real analysis 1, where we use the axiom of choice to construct, quote unquote, a non-measurable set. Well, you use the axiom of choice to guarantee the existence of a non-measurable set. And because you use the axiom of choice, you got no clue what's in it. Same problem here. I have no idea how to build a Hamel basis. It's nice knowing they're there. Every vector space has a basis. But if you're going to do something applied, this ain't going to be it, because you have no clue what's in this basis. You don't know how to build a basis for this setting. So that's a game changer. That's a, end of story as far as any sort of applications would go, which is why the story doesn't end here. What we need to do is say, Hamel basis, maybe there's a better kind of basis that'll give us more structure and stuff we can actually use, give us an idea to approach the question of what is a basis for this vector space and actually find a basis. And you do some of that stuff in sophomore linear algebra. The Gram-Schmidt process allows you to take a spanning set and create a nice basis, an orthonormal basis is what Gram-Schmidt does. We'll see Gram-Schmidt in here before it's over. So what we're going to do, because of this, uselessness of the Hamel bases, is we're going to modify some of the definitions we're using and generally just replace the idea of a finite linear combination with a series. But to do that, we got to be able to talk about limits, because series are limits. They're limits of sequences of partial sums. So we must have a metric to do this. Well, we need to be able to talk about limits, and you can weaken that structure a little bit and have simply a topology, and you can talk about limits in a topological space setting. And we'll do so with something called a Schauder basis. So let V be a vector space with metric M. A countable set of vectors, B, subset of V. So B, a countable set of vectors, is called a Schauder basis for the vector space if every vector in the vector space can be written as some series representation of the basis vectors. That is, every vector V is a sum from n equals 1 to infinity of f sub n, b sub n, where the b sub n's are in this basis B, and the f's are a countable collection of scalars as appropriate. So in some sense, somewhere under this is a linearly independent spanning set. But we're taking not finite sums anymore, but infinite sums. What role does the metric play? In making sense out of the infinite sum of the series. So what this means is, if we take a limit as n approaches infinity of the distance, the metric m, the distance from vector v to a partial sum, we get 0 out. You can make the partial sum as close as you want to vector v by making n sufficiently large. That's exactly what it means to have this series equal that value, that vector v. Some important words were Schauder bases are countable. Okay, that's an infinity, but it's the smallest infinity there is, so that's useful. The claim was also, maybe I didn't emphasize this enough, there's a unique collection of scalars in order that determines the vectors. That uniqueness implies the linear independence. If we wrote the 0 vector as, I won't call this a linear combination under the new rules, the rules of having a Schauder basis. If you write the 0 vector as a sum of all these b sub n vectors, then it must be that the scalars are 0. This occurs if and only if the scalars are 0, because I can take the scalars to be 0. That gives me the 0 vector, but the scalars are uniquely chosen under the rules of a Schauder basis. Well, that means linearly independent. Take the linear combination equal to 0, the coefficients must be 0. That's linear independence. Though I'm taking liberties with the term linear, that's the reason I got them in quotes here, that's not a linear combination in the traditional sense. Yeah, but this is too useful to let go of. We're going to modify the definition of linear combination to include infinite linear combinations. It'll take a little more structure, but that's the plan. It'll take a metric to do this. Little kind of sad historical note about Julius Schauder, for whom Schauder bases are named. He was born in, today it's in the Ukraine. At the time he was born in an area of Poland. He was drafted into the Austro-Hungarian army after he finished high school in 1917. He was taken prisoner in Italy. After the First World War, he entered Jan Kazimierz University, earned a doctorate in 1923. Others had studied bases of infinite dimensional spaces. This is a hot topic in the 20s. But Schauder gave his definition in English on the theory of continuous maps of functions or functional spaces in 1927. he studied topology, he studied functional analysis. I see him as a bit of one of the inventors of functional analysis. We're trying to work our way into Hilbert spaces, and the nice Hilbert spaces will be Hilbert spaces with a Schauder basis. So a lot of this Hilbert space, functional analysis, Schauder space, Banach space stuff, a lot of this is going on in the 1920s. Sadly, Schauder was Jewish. He died at the hands of the Nazis in 1943 in the Second World War. This little bit of biographical information is from the Mac Tudor History of Mathematics archive. Lots of dependable biographical information and historical information on some pretty esoteric topics in the history of math on the Mac Tudor site. But that finishes this first section of the Hong Wang and Gardner book, gets us on our way to dealing with infinite dimensional vector spaces and having the right kind of basis for infinite dimensional spaces. And the right kind of basis is a Schauder basis. We'll be talking more about Schauder bases. Hamel bases are an important part of the story, but that's not very useful stuff. So the the Hamel basis stuff, we've probably really seen the end of the Hamel basis stuff, but we certainly haven't seen the end of the Schauder bases. We'll make use of that and its useful stuff in lots of applications. So I'll see you in the next section. If this is the notes for the functional analysis class, we're probably going to go back and look at Schauder bases a little bit more. Otherwise, maybe move on to section 5.2 in the Hong Wang Gardner book. So all these videos are out there. I'll see you in the next one. Have a nice day.